we need to complete the second chapter of this optics, that is wave optics. Wave optics, we need to discuss wave optics. But see here, wave optics is another version of this optics. In this wave optics, mainly what we see is the complete propagation of wave in the form of the complete propagation of light in the form of waves. So there are two approaches to explain the propagation of light. Okay, so in one approach, the complete propagation of light is explained on the basis of waves. In the second approach, the complete propagation of light is explained on the basis of waves. On the basis of waves. But what do you mean by wave? This is what we must have some idea. But so I don't know whether you studied about this wave motion properly or improperly. I don't know. But okay, so let me give you some basic idea about the waves. But so what do you mean by wave? This is what we need to understand first. So what do you mean by wave? What do you mean by wave? A wave is nothing but the way how a disturbance in a medium propagates. A wave is nothing but the way how the disturbance propagates in a medium. How the disturbance propagates in a medium means, suppose you take this mechanism which is happening between you and me. If I don't talk, silence everywhere. The moment I start talking, what happens then? I am releasing the energy in talking. Got the point? So what about the energy which is released while talking? That energy will be propagating in the form of a wave. In the form of a wave. But so in doing so, in between you and me, air is there. Air particles are there. All these air particles will be receiving the energy. These air particles will be vibrating in a systematic way. By means of these vibrations, the energy is sent. The energy is carried from one point to the other point of the material, of the medium. Here, material means medium. Right? So the way how this energy propagates, that can be taken as wave. I will tell you the best example. Look at this here. So I will be taking water, not a river, just like a pond or any water body where water is not moving. Where water is not moving. But since the water is not in motion, so there will be complete pause. So what is it called? A kind of rest. You say all these water particles are stationary. There is no disturbance. There is no such thing. Complete calm. Water. But now what I do is I will be just taking one stone. So the stone I will be dropping from some height. The moment the stone touches the water surface, what happens? The moment the stone touches water surface, what happens? Immediately from this point, so this here one water ripple gets developed. Ripple, this is our common language. Ripple, this is the common language. But so the first, so water ripple gets developed. So in Telugu, this we say Allah. Allah. In Hindi also Al. Allah. That's a Hindi. I don't know this in Kannada, but Ale. Got the point? So that's here you see. This is one more ripple gets developed. Next, one more ripple gets developed. Next, one more ripple gets developed. Like this, these ripples will be spreading. Did you understand? These ripples will be spreading. So the formation of these ripples is nothing but wave formation. The formation of these ripples can be taken as the wave formation. In this wave formation, what happens? Here, the stone is dropped from this point to this point. The stone is moving. The stone has some mass and the stone has some velocity. By means of the motion, half mv square, which is a kinetic energy, is gained by the stone. So due to this motion, what happens? The stone will be having some kinetic energy. By means of that kinetic energy, the stone will be reaching the surface. The stone will be touching the surface. Then what happens? So at the time of this collision, this stone will be releasing the complete kinetic energy. So what about the water particles which are present here? All these water particles will be absorbing that energy. After absorbing that energy, what do these water particles do? These water particles start vibrating up and down. So this is a water particle. This water particle will start vibrating up and down. Up and down. So how can we say that water particle is vibrating up and down only? We can go for a small activity. So here you see, you take a small piece of paper. By means of paper, you just make one paper boat. You just make one paper boat. You just put the paper boat that's on these ripples. And what do you notice? So we can see that the paper boat will be just moving up and down. The paper boat will not go. And if at all the paper boat is going, means what happens? So that is due to air push. When there is no air push, got the point? So the paper boat will be there only. The paper boat will be just moving up and down like this. By means of this, what do you say? What makes a paper boat move like that? Water. Water means water particles. Got the point? So whatever the water particles which are present over here, these water particles will be moving up and down. So that these water particles will be making this paper boat move up and down. So ultimately, we can conclude that all these medium particles, here what is a medium? Water. All these medium particles, that is water particles, will be moving up and down, up and down. That is called vibration. That is called vibration. By means of this vibration, what happens? By means of this vibration, what happens? Look at this. Here you see, this is the medium particle. This medium particle is vibrating. But this medium particle will not go anywhere. Remember, the medium particle will not go anywhere. The medium particle will simply be vibrating up and down. But ultimately, energy will be going. In what way? This medium particle will transfer the energy to the next molecule. Even the next molecule also will be vibrating. But so this next molecule will be transferring the energy to the next. Even this molecule will be vibrating. So this molecule will be giving that energy to the next. But so from one phase to the other phase, the energy is being transferred by means of all these molecules. But no molecule undergoes displacement. Where the molecule is, molecule will be there only. Okay, so from its own position, the molecule will be just vibrating. But so by means of these vibrations, ultimately, energy gets reflected at some other place. Energy gets reflected at some other place. But this is called wave motion. So during the wave motion, what we have to notice is, okay, the medium particles will not go anywhere. Where the medium particle is, the medium particle will remain there only, but the medium particle will be exhibiting the vibrations or oscillations, whatever it may be. By means of that, okay, energy will be passing from one point to the other point of the medium. That is called wave motion. So ultimately, without medium particles linear motion, the energy is carried from one point to the other point. That is called wave. That is called wave. But now I will give you one more example with which you can be so clear. Okay, so look at this again. I will give you an example. Okay, so this is a new movie is released. KGF Chapter 2. KGF Chapter 2 is released. Right? You think that there is no online booking, there is no there's what is it called? There's a book by show that okay, that and all are there. If at all you want to watch movie, you need to go to theater, you need to stand in the queue, old method. You need to take the ticket, only that is there. Imagine. Okay, so look at this here, you see. You see here. So this is okay, booking counter. Got it? This is booking counter. Right? So this is opening, small opening will be there. Okay. So this is here. So this he is the person. Okay, so he's giving the tickets. Okay. Right? Okay, so he's the person who is giving the tickets. Ticket seller. Ticket counter. Right? Imagine that Gulbarga people are very obedient, very disciplined. Not like crowded. Okay, now see here. So one person stood over here. Another person stood over here. Okay, so another person over here, another person over here, another person over here, another person over here. You make it. Okay, because new movie, no, KGF 2, because we have been waiting for that. Not only here, there's even Hyderabad also, people are eagerly waiting for KGF chapter 2. KGF chapter 2. Understood? Okay. So there's in that group, even my daughters are also there. They are eagerly waiting when KGF 2, when KGF 2. Huh? Okay. So all possible trailers, so official trailers, unofficial trailers, all the things they are covering up. Got it? Okay. So this here, all the people are standing over here like this. All the people are standing over here like this. Okay. Now just imagine. Okay, very close. Very close. Okay. Now, so this fellow, our Mayur came. And what he did was, okay. Okay. Right. Okay. So this fellow, there's a Mayur came. Just he went to the back. He gave a push. He applied the force. But yeah. Okay. So he applied force. But again, okay. Now, till the force is applied, there was no disturbance. All the people nicely happily they stood like this. Yes or no? The moment he applied the force means he's giving the energy. The moment energy is given to that, to this last fellow, oh, Mayur has given me that energy. Okay, I have to move. So there's a way. So will that fellow come out and will that fellow run out? Tell. So he will not come out. Okay, so he will be here only. And what will he do? By means of this push. So this fellow will be moving back. Got it? So by means of this moving forward, he will be pushing this fellow. Okay, so in doing so, first he will push this fellow and he will move back. Means like this. So this fellow will exhibit a kind of movement like this. By means of this movement, again this fellow, what will he do? So this fellow will, fall forward and he will be pushing this fellow and again back. Got the point? So in this way, what happens ultimately? All these people will be just moving forward, backward, like this. Are you getting my point? Okay, ultimately, whatever the energy he supplied here, the energy will get reflected here. And if at all, the push is very heavy, got it? This first fellow will get crushed to the counter. This first fellow will get crushed to the counter. If at all, you apply that much force. But, so that's a Mayur did not apply the force here. Where did he apply the force? He applied the force there. But ultimately, the force and the energy got reflected here. Are you getting my point? Okay, how does energy get reflected over here? All these people will be just vibrating forward, backward, forward and backward. Got the point? In that way, so this here you see. So giving energy, push. What is this? Disturbance. And what about the disturbance which is created in this? What do all these people indicate? Medium particles. Medium particles. Whenever the disturbance is given like this, all these medium particles will be vibrating like that. All these medium particles will be vibrating like that. By means of these medium particles vibration, ultimately the energy gets reflected. That's at the other end. So this is the wave formation. And in this complete mechanism, these people are not coming out of the queue. These people are not running out. Where the person is, the person is there only. Got the point? Only the person will be just moving. That's all. Vibrating. How these people are moving forward, backward. By doing so, how the energy is getting transferred from one point to the other point. In that way, medium particles also vibrate. Got it? And the medium particles will be transferring energy from one point to the other point of the medium. This complete mechanism is nothing but wave motion. This complete mechanism is known as wave motion. Now you can understand that. So the movement of these people you can see, but the movement of the medium particles we can see. Ultimately, one thing we can experience. What is that? The energy propagation. The energy propagation. Okay. So by means of all these observations, how can you define the wave? Wave is nothing but the way how energy gets transferred from one point to the other point of the medium. The way how disturbance propagates in a medium from one point to the other point. Jewel, dear. Jewel. Okay. Are you okay? Okay. Right. So this is from one point to the other point of the medium. One point of the other point of the medium. How the disturbance propagates, that can be taken as wave. But okay. So whatever the wave, whatever the waves that we have to discuss, that we are discussing, this, in fact, all these waves are classified into two categories. Waves are two categories, right? So here you see, some waves are known as mechanical waves. Some waves are known as mechanical waves, and some waves are known as electromagnetic waves. Okay, another category of waves is also there, that is matter waves. Okay, broadly speaking, the waves are of three categories. So some waves we will be calling as mechanical waves. Some waves we will be calling as electromagnetic waves. And some waves we will be calling as matter waves. Matter waves. Understood? Okay. So about matter waves, we are not going to have discussion now at this moment. About this matter waves, we will be discussing in dual nature of radiation and matter, and some part in the atoms chapter. In those two chapters, we will be discussing about these matter waves. Even that is also I only teach. Next session, next week is so that discussion. But okay, so about electromagnetic waves, already briefly I told about Maxwell's discovery and other things. Okay, so about mechanical waves. Mechanical waves means energy will be given by means of mechanical form. We know that mechanical energy is of two types. Mechanical energy of two types. Okay, one is potential energy and the second one is kinetic energy. One is potential energy and the second one is kinetic energy. By means of one of the forms of energies, when the wave is produced, that is called wave motion. And whatever the example I have taken, two examples I have taken. One is water. The second one is people are so who are in queue. But the point, okay, that's in both the cases. How is the energy given? Mechanical. In the case of a stone, stone is falling down. Kinetic energy, mechanical energy. Mechanical energy. So whatever the waves which are getting developed on the surface of water, those waves are nothing but mechanical waves. And whatever the wave which is passing among the people, when the push is given at the back of the queue, okay, even the thing also is a mechanical wave. Even the thing also is a mechanical wave. So you take a rope, okay, you hold it properly, tightly, okay, at one end, you just give it a jerk. Then what happens? So there's a wave, okay, it gets it. Okay, only jerk, not there's a jaws playing, such an, okay, there's a, okay, jaws, drums, not drums playing, only one side jerk, that's all. Not two sides. Okay? Guitar. Okay. There are some waves that so get produced. Right? Okay. So this here you stretch the string. Get one side, just give you a jerk like this. Then immediately there's here a kind of wave gets propagated. Understood? Okay. So this here, how are you giving the jerk over here? So by means of mechanical energy. So this is mechanical wave. This is mechanical wave. Only one thing you remember. Whenever the wave is produced out of mechanical energy, that is called a mechanical wave. That is called mechanical wave. But next, electromagnetic wave. Yesterday I explained. So electric field will be oscillating, magnetic field will be oscillating. By means of the oscillations of electric field and magnetic field, the wave is created, the wave is generated. That is called electromagnetic wave. This mechanical wave needs medium. Without medium, these mechanical waves will not propagate. Those electromagnetic waves don't require medium. even in the absence of medium, these electromagnetic waves will be propagated. And about the matter waves, now I am not going to get into the topic. But so it's okay. Origin is quite different. But okay, now look at this again. You see, so whatever it may be, mechanical wave you take, electromagnetic wave you take, or matter wave you take, all these waves will be of two natures. Okay, so what is the nature of these waves? Okay, so look at this here, waves. Some waves will be in this nature, that is longitudinal. And some waves will be transverse nature. Some waves will be transverse, by nature. So what do you mean by longitudinal and what do you mean by transverse? Longitudinal nature in the sense that completely depends upon the way how the medium particles vibrate. Okay, so during the wave propagation, see, there is a wave which is moving in this direction. But when the medium particles vibrate parallel to the propagation of the wave, that means if this is the medium particle will be vibrating like this. Okay, in doing so, look at this here. You see, there will be some particles over here. There will be some particles, sir. Now, if this medium particle vibrates like this, look at this. Okay, look at the board. Here, these are the particles. My 4 fingers are the particles, medium particles. This is one more medium particle. Okay, the moment energy is given, what happens, sir? So this will be moving like this. When this medium particles moves like this, what happens then? All these medium particles got compressed. Okay, then immediately it will come back. Like this. Okay, so when they relax, so whatever the particles here, they get compressed. Yes or no? Again they relax. When they relax like this, whatever the particles which are present, they get compressed. Now did you understand? Okay, so this here, so during the vibrations of these medium particles, when the medium particles get relaxed, the other medium particles which are in contact with those medium particles get compressed. Again, okay, so they will get relaxed because of elastic nature. Because restoring forces act. By means of these restoring forces, again these medium particles will be coming back. Okay, so that's when these molecules get relaxed. The other medium particles which are in contact with that, again those medium particles get compressed. Akhilesh. Medium particles get compressed starting. There was an initial stage. Understood? Okay. Okay. After food, this is all the situation. After food, the class in the sense of very painful. Have you get it? Yes or no? That's why there's a Sundays. We kept after lunch, no classes, happily sleeping. After your arrival, even that thing also has gone. Even after lunch also, you are taking the class. What, Maheshwari? Calculated? Yes, absolutely. Okay. Yes or no? How nicely we used to sleep Sundays? How nicely we used to sleep? So those days you used to take the class before lunch, 1 to 2, or 12 to 2 something. But then we used to wait eagerly to go to bed, not for lunch, to go to bed. Yes or no? Okay, now that has gone. In the new schedule. Right. See, what I'm telling is during these vibrations, the medium particles will behave like that. In doing so, yet some places, when medium particles move away from each other, yet some other places, medium particles will get compressed. Okay, so compressions and rarefactions take place. Abhishek, this much he opened. Just like crocodile. Just like crocodile. Okay. What Abhishek? Okay? Fine? Yes. Good, very good. Okay? That the curd rice is there, no? Curd rice, have you taken a lot? So there is a reason. You didn't take. Even then, started. Okay. Right. Good, very good. So the compressions and rarefactions take place over here. So by use of this, here you see the medium particles get relaxed over here. At some other places, medium particles get compressed. At some other places, the medium particles get closed like this. So this is the way how the wave propagation takes place. So these are called compressions, these are called rarefactions. This is compression, this is rarefaction. Compression, rarefaction. Got it? Okay, so if at all you take any two consecutive compressions or any two consecutive rarefactions, that is equal to wavelength. Wavelength is represented by lambda. So this is wavelength. Wavelength we see, which is measured in terms of meter SI units. That is related to distance. Okay, the distance between two particles which are in the same phase, that is called that's suppressed. He got the yawning unit. Okay, so the thing also technique. Okay, that's the first he got yawning. And there will be some people, look. By closing mouth only. Yes, I know, so many techniques. So many techniques. Okay? Yes. Covering up. We have to cover it up now. Right. Okay? So this is called wavelength. So wavelength in the sense that is the distance between any two consecutive points which are in the same phase. There's a compression. These two things will be in the same phase. Rarefaction and rarefaction. These two things will be in the same phase. Understood? Is that all? So that is called wavelength. Okay. So this is something about longitudinal wave. Usually, what are the best examples of these longitudinal waves? Sound waves. And what about the sound waves which are propagating now? These sound waves will be nothing but longitudinal waves. Right? So when I talk, you are getting the voice. Sound. How? In what way? So what about the air which is present between your ear and my mouth? The air undergoes a kind of vibration. All these vibrations will be in this way. All these vibrations will be in this form. Right? Ultimately, these vibrations will enter your eardrum. That will be vibrated. And according to the frequency of the vibration, our brain will analyze what kind of sound you are observing. The whole mechanism takes place within the fractions of seconds of time. This is how the sense of hearing takes place. Right? Okay. Now, the second category of waves, transverse waves. And in the case of transverse waves, what happens? In the case of transverse waves, what happens? So the wave ultimately is propagating like this. This is the axis of the wave. Each and every medium particle vibrates today perpendicular. Okay, each and every medium particle vibrates like this. This is the way how the medium particle vibrates. This is the way how the medium particle vibrates. Ultimately, you will be getting so much distortion of the waves. Ultimately, so you will be getting this distortion of the waves. Okay, so how are these vibrations obtained? These vibrations are perpendicular to the propagation of the wave. These vibrations are perpendicular to the propagation of the wave. Whenever the wave formation is like this, that is called transverse wave propagation. Transverse wave propagation. In this transverse wave propagation, so this is one point which is getting extreme vibration, which is called crest, and this is a trough, and this is a crest, and this is a trough. Crest to trough, crest to trough. Right? Now the distance between two consecutive crests and two consecutive troughs, so that is known as wavelength. That is known as wavelength. That is known as wavelength. Right? So this is the brief introduction of these waves. Now, in these categories, what type of waves we have to apply for light propagation? Yesterday, I was telling you, what is that? Christian Huygens propounded the wave theory of light. But according to Huygens, these waves are longitudinal by nature, not transverse. transverse approach was given by Maxwell in his electromagnetic wave theory. Remember, in his electromagnetic wave theory, he gave the transverse nature, electromagnetic wave nature, other things. But according to Huygens, light waves are longitudinal mechanical waves. Longitudinal mechanical waves. Okay, now in this regard, we need to understand one point proposed by Huygens, that is wavefront. That is wavefront. Come on, keep the heading. Wavefront. What do you mean by wavefront here? Come on, then. Wavefront. Wavefront. What do you mean by wavefront? Very simple. Wavefront means, look at this here, you see. So if you take any point source of light, in the previous example, water. See, this is the surface of water. When you drop a stone from some height, the stone will be carrying some energy, which is nothing but kinetic energy. By means of some kinetic energy, the stone will be touching the surface. The energy carried by the stone will get liberated at once. Then all the medium particles will be just absorbing that energy. The medium particles are vibrating. So you will be getting one ripple over here. Okay, so this ripple, you just see the shape of this ripple. So this ripple can be taken as wavefront. This ripple can be taken as wavefront. Yes or no? So this becomes wavefront. Next, one more ripple is getting developed. This is wavefront. One more ripple is getting developed. This is wavefront. Wavefront means what? What do you mean by wavefront? See, this is the locus. This is the envelope of all these medium particles. Alright? So on the water surface, when the ripples are produced, when the ripples are going in a particular direction, do you see the actual vibration of each and every medium particle? Tell me. Here, ultimately, all water particles are vibrating. But will you be able to see the vibrations of these water particles physically? No. What about the ripple ultimately that you are going to see? That is nothing but the combination of so many millions and billions of water particles which are exhibiting vibrations. Exhibiting vibrations. Are you getting my point? Okay, so in that way, the shape is observed. Ultimately, whatever the shape that you are getting, that is called wavefront. What is that shape? That is nothing but the connection, locus, envelope of all vibrating medium particles which are in the same phase. That is called a wavefront. That is called wavefront. Wavefront means that is the locus of all vibrating medium particles. Locus of all vibrating medium particles which are in the same phase, that can be taken as wavefront. That can be taken as a wavefront. Okay, so look at this here. You see in the space, these are the medium particles. Now this is the source of light. The moment the source gives out the light, all these medium particles start vibrating. Why am I showing the vibrations in this way? Because light waves are longitudinal by nature, according to Huygens. Of course, that was disproved, but to some extent, longitudinal nature will be seen. Right? Okay, so the if you connect all these extremities like this, then you will be getting the locus. And whatever the locus, whatever the envelope that you got, which covers all these medium particles vibrating in the same phase, that can be taken as a wavefront. That can be taken as wavefront. Right? So what will be the shape of the wavefront? That completely depends upon the shape of the source. If at all you take the point source of light, the wavefronts which are spread out in the space, they will be spherical. One sphere gets developed, one more sphere gets developed, one more sphere gets developed, one more sphere gets developed. Like this, in this concentric spheres, one after the other, one after the other, wavefronts are developed. Those wavefronts will be passing by. But in that way, the illumination of the complete space takes place from the source of light. That is the way how the propagation of light takes place. That is the way how the propagation of light takes place. What about the shape of these wavefronts here? Spherical wavefronts. From the point sources, you will be getting the spherical wavefronts. Okay. Now, one more category is also there. That is a plane wavefront. So, what do you mean by plane wavefront then? Plane wavefront. Plane wavefront is nothing but a small portion of a spherical wavefront. See, if you take, yeah, there's a sphere or circle of small radius you take. Now, what I do is I will be just taking some small portion of here on the circle or on the sphere, anything. Okay, so if you treat this one as a circle, when you take a small portion, the small portion appears to be like this. Am I correct? Can you take this portion as a straight line? No, it's a curve. Now I will be taking, okay, so this is a sphere or circle of large radius. You take this one. Now same length of portion I have taken. Now what about this? Now how does it appear? It appears as a line, a straight line. If at all you take as a circular one, this becomes a straight line. And if at all you take a sphere, then it looks like a flat, plane. See, very simple. Look at this here. You see, okay. Now this is if at all you stand here. Suppose now I am here. Okay. Now this is some height I am standing. Now this I am just looking at the surface of the earth. For me, how does the surface of the earth here till my eye goes? But one, okay. How does it look like? Flat on it. Flat. Do you know one thing? In the olden days, some thousands of years ago, people used to consider that Earth is flat. Do you know that? Earth is just like a flat. Some thousands of years ago, this was the assumption. Flat in the sense of, okay, so there will be some end of the Earth, and if you go, there will be, that's here you will fall into space. So you should be very careful. That's why you should not go anywhere. Like that, people used to get restricted. True, this is true. People used to think that Earth is a flat. So do you know this how? Okay, they came to know. They might have gone by flight or rocket. Then the moment you go into space to some height, then automatically the Earth appears like a sphere. Sir. No, those days where was the aeroplane? Where was the rocket? So aeroplane was not invented. Even then, people came to know that Earth is not flat. Do you know there's on what basis? Do you know what there's on what basis? Those days, people used to sail. By ships. But the older ships, there's the handmade ships used to be very gigantic. So Pirates of Caribbean. Ships, handmade ships used to be there. By means of this here, the moment they enter into the sea, some months, some years, they will be in the sea. Got it? So here you see, if at all the sea, the ship, comes to the shore. See here. So look at this. If at all Earth is flat like this, right? So this is the sea. So a person is standing over here. Right? Ship is coming. Ship is coming like this. Right? When the ship approaches, how does ship appear for this person? Complete ship has to be visible. Am I correct? And whatever that there's a here. So there's a what is it like that pillar, that pipe, and the smoke, and everything. Everything that's here has to see. When the ship is going, there's here some smoke also will be giving. So it is given up now, just like a train engine, old train engines. Understand? Everything should be visible. But people observe that it is not visible like that. And what happens is here you see, so this is here, also that's you can see. When the ship comes to the shore, just stand at the shore and you keep observing. What will be visible first? Only some smoke will be, that's the visible. Some smoke, where the smoke is coming, that's whatever that, then the top end, tip of that pipe, smoke pipe, will be visible. Yes, it comes. So the length of the pipe will be increasing. But then slowly, okay, the top portion of the ship will be visible. Slowly, the complete ship will be visible. Why? Because of line of sight. Line of sight, look at this. Okay, so this is here. Ship is coming this side. So this is the ship. This is the ship, you said, like this. Okay, so the observer is here. When, okay, line of sight. Line of sight. There is a line of sight. But okay, now at this moment, ship will not be visible. The moment the ship enters over here, then, so this is the smoke. Smoke will become. The smoke, so this is smoke will be visible. Next, the moment ship comes over here, okay, so this is supposed to be here. This will be visible. But the ship will not be visible. But later, the complete ship will be visible. Okay, so this type of observation in the olden days, people kept on making. Why? The ship appears to be like that. When Earth is flat, the complete ship has to be visible now at once. Why? Only the top portion. Slowly, we are observing the complete ship. Means Earth is not flat. Earth has got some curvature. But again, so like that, they developed the idea. Understand? So what I'm telling is, see here, if you take a large sphere, in a large sphere, when you take a small portion, that small portion appears to be a plane, almost. But the kind of plane. Yes? Okay, so that is the plane wavefront. Plane wavefront means it's a small portion of a spherical wavefront with a large radius. A small portion of a spherical wavefront of large radius that can be taken as a plane wavefront. So this is the second category, right? Next, the third category of wavefront is also there. That is a cylindrical wavefront. The third category is also there. That is cylindrical wavefront. So what do you mean by cylindrical wavefront? Usually, the cylindrical wavefront is produced by the extended sources of light. Extended sources of light, just like a slit. Even the tube light also acts as, okay, so cylinder gives out the cylindrical wavefronts. And if at all, so the source is like this in this way. This is the source. Then, so from this one cylinder gets the wavefront, and one more cylindrical wavefront. Next, one more cylindrical wavefront like this. So in this way, so the wavefronts are produced. In this way, the wavefronts are produced. So like, okay, so in that way, the wavefronts are produced. Cylindrical wavefronts. Cylindrical wavefronts. Cylindrical wavefronts. Right? So this is the concept of wavefront. Now, in this regard, you need to understand one more thing. Primary wavefront and cylinder, that's a secondary wavefront. Primary wavefront and secondary wavefront. So what do you mean by primary wavefront? What do you mean by primary wavefront? Next, secondary wavefront. Okay, secondary wavefront. Secondary wavefront. Primary wavefront and secondary wavefront. Primary wavefront means, look at this here, you see. So this is the source. Okay, primarily, what about the wavefront which is developed over here? Spherical wavefront. So this can be taken as a primary wavefront. Now, Huygens practically showed one thing, that what about the points present on, okay, each and every point on the primary wavefront acts as a secondary source of light. In what way? Look at this. This is the point. From this point, okay, another wavefront gets developed. You take this point, from this one more point gets developed. You take this point, one more wavefront is developed. Actually, so this is sphere. Okay, one more sphere like this, and one more sphere, and from this, one more sphere, and from this, one more sphere. Each and every point of the primary wavefront behaves as a secondary wavelet. Now, the envelope of all these things, if at all you take, this becomes a secondary wavefront. This secondary wavefront is also known as a secondary wavelet. This is also known as secondary wavelet. Okay, so the secondary wavelet gets developed even inside now. Inside the primary wavefront, also secondary wavelet will be there. But at the same time, one more primary wavefront will be there. From this, okay, so one more secondary wavefront will be coming out. And because of the forward push of these secondary wavelets, whatever the secondary wavelet that you are getting for this primary wavefront, that gets vanished because of superimposition. Ultimately, so this wavelet, okay, is seen that it is advancing in a particular direction. This wavelet is seen that it is advancing in a particular direction. But so this is the concept of primary wavefront and secondary wavelets. Right? Secondary wavelets. Are you clear with this point? And if you take any plane wavefront, so look at this here. You see, this is the plane wavefront. So plane wavefront means that is not something else. That is not something different. The plane wavefront is nothing but a small portion of a spherical wavefront. That will be the plane wavefront. Now, yes, Huygens told each and every point of this plane wavefront also behaves as the secondary wavelet, secondary source of light. Secondary source of light. So in that way, so look at this here. You see, one sphere gets developed, and again one sphere gets developed. Again, one sphere means what do you mean by the spheres? They are secondary wavelets. Now, if you join all these things, some secondary plane wavefront gets developed. So that will be advancing in this direction. That will be advancing in that direction. That is the concept of secondary wavelet and primary wavelets. Ultimately, in the space, the complete propagation of light takes place with the combination of these primary wavefronts and secondary wavelets. By the combination of primary wavefronts and secondary wavelets. Understood? So this is the concept of wavefront. Are you clear with this point? Yes or no? Yes. Now coming to the next thing. So Huygens' explanation for reflection. In that we come across some equations, small equations we come across, right? Huygens' explanation for reflection. So reflection. So look at the word, try to understand it. Huygens, how did he explain the reflection that takes place in the case of light? See, reflection means rebounds in nature, everybody knows. Earlier, that is in the ray optics, we studied this reflection in terms of ray, light rays. Now, we will be discussing this reflection in terms of waves. In what way? Look at this here, you see, this is the reflecting surface we have taken. So, this is M and N. This is reflecting surface, imagine. Okay? Now, there is a source present over here. Let this source be emitting out spherical wavefronts. In those spherical wavefronts, I will be taking a small portion. Then it becomes a plane wavefront. Let this be the plane wavefront which is approaching like this. This is the plane wavefront which is coming like this. This is the plane wavefront. This is AB. AB is the plane wavefront. Okay, so this plane wavefront, look at the board. This plane wavefront is just moving like this. Like this, the plane wavefront is moving. The moment this plane wavefront comes in contact with this, look at this, the corresponding rays will be like this, perpendicular to this. And this is one more ray perpendicular to this. This is one more ray perpendicular to this. This plane wavefront is making some angle with the reflecting surface, that is theta, or that is the angle of incidence I. Okay, now in this plane wavefront, we can imagine so many points. Each and every point will behave as secondary wavelets, secondary source of light. So the secondary wavelets will get emitted out from each and every point. From each and every point. Understood? Okay, now A has already come in contact with this reflecting surface. So reflection begins. Right? But what about the point B over here? Point B has to cover still this much distance. Am I correct? Point B on the plane wavefront, incident plane wavefront, point B has to come in contact with the reflecting surface. To do that, this much distance has to be covered at. Are you getting my point? Okay, so what is the distance covered by this secondary wavelet? Secondary wavelets are produced. These secondary wavelets are moving in this direction. These secondary wavelets will be taking some time t, you say. So this is the point D, you say. The velocity of light in air or free space C, you say. Then what will be the distance between B and D? Velocity into time is equal to distance. So C into T, that much distance is covered by the secondary wavelets to cover the distance between B to D. To cover the distance between B to D, the distance covered by secondary wavelets is C into T. Are you clear with this point? In the meantime, what happens? Okay, so will the point A keep quiet? Anyhow, the secondary wavelets are going. Okay, let them go. Why to hurry? So in the meantime, I will take a nap like this. Over. Shall I start? Can I start? Like this, will the point A be? No, it won't be like this. Yes or no? Okay, so this here you see, when the secondary wavelets are coming from this A, there's a B to D. In the meantime, the secondary wavelets from A, so they start getting reflected. Okay, so when the secondary wavelets cover this much distance, at the same time, the secondary wavelets from A, so will undergo reflection. These secondary wavelets will keep moving like this. Yes or no? So at a given time t, so how to estimate the position and the shape of the secondary wavefront, which is from A. For that purpose, what we have to do is, we need to take the C into T as a radius. We need to take the point A as center. You need to draw a sphere. Draw a sphere over here like this. Right? Now, from the point N, you need to draw a tangent. This is the tangent on this. To this tangent, if at all you draw perpendicular, this is nothing but radius. Got it? So this is also equal to CT. Right? This is A and to E. Okay, so this is the reflected plane wavefront. This is incident plane wavefront. This reflected plane wavefront makes an angle R, which is called angle of reflection. Are you clear with this point? According to Huygens wave theory, the angle of incidence, the angle of reflection are like this. Got it? Not the angle between the normal to the incident ray, normal between the angle between the normal and the reflected ray. That concept we do not apply over here in the wave concept. Understood? Directly, that is the angle made by incident plane wavefront with the reflecting surface. Reflected plane wavefront by the reflecting surface. That becomes the angle of reflection and the angle of incidence. Now, how to bring out the loss of reflection? Okay, so look at this here. You see, whatever the plane wavefront which is coming, that is perpendicular to the plane of the paper. Whatever the plane, there's a reflected wavefront which is obtained, even that thing also is perpendicular to the plane. Okay, so the first law is moving. Now coming to second law. The angle of incidence is equal to the angle of reflection. How to bring out? Look at this. Here you see, if you see this figure carefully, there are two triangles that you can see. Triangle ABD, that is one triangle, and a triangle AED. Am I correct? What about these two triangles? What can you conclude? What do you say about these two triangles? Triangle ABD, triangle AED. Look at this. These two triangles have got the common side AD. What is the common side? Hypotenuse. Look at this. This is a right angle. Even this is also right angle. And coming to this BD and AE, both the things are same because you have drawn the sphere by taking CT as radius. Got the point? By RHS. What is that? Similarity, congruency. RHS. RHS rule, right angle hypotenuse side, congruent rule. Congruent rule. By RHS congruency rule, okay, so triangle ABD is congruent with the triangle AED. Understood? Okay, so congruent triangles means in all the aspects. Okay, so this is their measures are same, the angles are same, sides are same. That is called congruent. That is called congruent. Okay, so by use of this, what do you say? The angle BAD is equal to angle. Here this is ADE. ADE. The angle ADE. Okay, by CPCT. Corresponding parts of congruent triangles by CPCT. Understood? Therefore, what is the angle BAD? I. What is the angle ADE? I is equal to R. This is what Huygens' explanation for reflection. Briefly, note it down. Free hand. Come on, please make it faster. Yes, over. So this is something about reflection explained by Huygens. Now refraction we need to take. Yes. Okay. So refraction we need to take. So what do you mean by refraction? Explained by Huygens. Huygens refraction. You know one thing very well, that refraction is a phenomenon in which light passes from one medium to the other. Okay, so when the light passes from one medium to the other, it will be just exhibiting a kind of bending effect. But remember, what about the two media that we are going to take up? The two media must have difference of densities. One medium must be at some density, the other medium must be at some other density. But find there must be some density variation by means of which one medium becomes a rarer medium and the other becomes a denser medium. Okay, now refraction by Huygens wave theory. Refraction by Huygens wave theory, or simply we say Huygens refraction. Huygens refraction. Okay, now refracting surface I will be taking. I am taking air over here. I am taking glass or any other denser medium. Now look at this. Here you see, this is the source of light. Usually from the source of light, spherical wavefronts are emitted out. I will be taking one plane wavefront like this. This is a plane wavefront, which is AB. Now this plane wavefront is coming like this. With the speed, okay, velocity of light in air, c. Now this plane wavefront is coming like this, like this, like this, like this. The plane wavefront is touching the surface. The moment plane wavefront touches the surface, it will be like this. This is A and this is P. What do you say about corresponding light rays? This is one light ray, and this is one more light ray, and this becomes one more light ray. Right? Now the point A on the plane wavefront has come in contact with the interface, surface. But what about the point B? Still the point B has to cover some distance. And what is the distance point B has to cover? Perpendicularly. So secondary wavelets are covered. So these are the secondary wavelets. These are the secondary wavelets. All these secondary wavelets will be simply passing over here like this. From B to D, the secondary wavelets came. What is the distance traveled by the secondary wavelets from B to D? C into T. C into T. That gives you the distance covered by the secondary wavelets from B to D. In the meantime, what about the secondary wavelets from A? Will they keep quiet? Still, okay, so till the complete process get over, will they keep quiet? Well, no, they will not. The secondary wavelets will begin. In the same amount of time T, okay, so the secondary wavelets will be passing from this. But the thing is, okay, this much distance they will not be able to cover because this is denser. In the denser medium, the speed of wave decreases. Right? Okay, so this here, so this, okay, so we'll be able to cover only this much. The speed of light in this denser medium, V, then V into T, this is what? The distance covered by the secondary wavelets from A to this. Now, how to estimate the position of refracted wavefronts? How to estimate it? So by taking this Vt as radius, okay, so by taking A as center, you need to draw a sphere. To this sphere, from D, you need to draw a tangent. You need to draw a tangent like this. And whatever the tangent that you are drawing, this represents the second, that's the here, refracted wavefront. Refracted wavefront. Right? Okay, so this is making an angle R, which is the angle of refraction. This is making an angle that is I. Are you clear with this? Once again, I repeat, AB is a plane incident wavefront. When AB touches this interface, point A only has come in contact with the refracting surface. But point B, okay, so he is away from this. From point B, secondary wavelets are produced. These secondary wavelets will be covering this much distance. These secondary wavelets will be reaching the point D. The distance traveled by these secondary wavelets is written as C into T. In the meantime, same time, secondary wavelets from A will begin into this glass. But these secondary wavelets from A will not be able to cover this much distance. They will be able to cover only this much distance. How much distance these secondary wavelets are covering up completely depends upon velocity. More the velocity, more the distance covered will be. Lesser the velocity, lesser the distance covered by the waves will be. Understand? Okay, so once again the distance is covered like this. Let it only be T. Now you need to estimate the position of this refracted wavefront. For that purpose, what we do is you need to draw a sphere. To that, that's the sphere, Vt as radius, A as a center. Now, from this D, you need to draw a tangent. Whatever the tangent you have drawn here, that tangent represents the refracted wavefront. Refracted wavefront. Now look at this, there are two triangles over here. This is the right angle triangle, even this is the right angle. Triangle ABD and triangle AED are formed. Are they congruent now? Are they congruent? Tell, are they congruent? No. Not at all congruent. Okay, so what I do is I will be taking sin I. Opposite by adjacent, the opposite by hypotenuse. What is hypotenuse? AD. And sin R I will take. Opposite by hypotenuse. Sin I by sin R. Sin I by sin R. Okay, so AD will get cancelled. C, TT and will get cancelled. So this is C by V. This is how another formula we get for refractive waves. C stands for velocity of light in wave. V stands for velocity of light in the given medium. That could be glass, water, or any other medium. That could be glass, water, or any other medium. Snell's law is optic. Snell's law is optic. Understood? Come on, go down. Where is Sakshi? Even yesterday also she was not there in the classes. She went home. Yes, hold on. Right. Okay. So this is something about Huygens refraction. Over, note it down, everybody. Please make it faster. Yes. Okay. By means of this Huygens, I'm erasing. Over, not over. Over. Yes. So by means of this wave theory, Huygens he could explain. I think this is over. Puja. Over. Roach. Very good. Yes. Huygens he could explain reflection of light successfully. Refraction of light also successfully. Next, interference of light also he could explain. Even diffraction of light also he could explain. But he was not able to explain polarization. Polarization. But the point, not only polarization, the remaining concepts are also there. Just like photoelectric effect. Photoelectric effect, this is one effect which was not explained by Huygens wave theory. Okay, next, Compton effect. Compton effect. Next, Raman effect. Raman effect. Understood? So these effects. Okay. So next, dispersion of light. Dispersion of light. So these are the things which were not explained by Huygens wave theory. Which were not explained by Huygens theory. So these things can be taken as limitations in Huygens wave theory. These things can be taken as limitations of Huygens wave theory. They were not explained. Got it? Okay. Now interference and diffraction also we have discussed. Now the next discussion will be interference. Interference. To understand this interference, first of all, you need to understand something about superposition of waves. Superposition of waves. Superposition of waves. You need to understand something about superposition of waves. So what do you mean by superposition of waves? When waves from different sources are taken together very close to each other, the waves get mixed up. And the mixing effect of those waves can be taken as a superposition. The mixing effect of these waves can be taken as a superposition. Now, how do these waves undergo superposition? This is what we need to think of. See here, look at the board. I am taking one source of light, that is S1, and I will be taking one more source of light, S2, over here. Now, from S1, one light, this wave is coming out like this. Okay. In general, I am saying, there's a longitudinal wave also happens the same thing. Okay, to make you understand very clearly, easily, I have taken transverse wave. Okay, so this is a crust you take, this is a trough, and this is a crust. This is a trough. And by means of this crust, what happens? If you take the medium particles, this medium particle is made to vibrate in the upward direction, like this. So because of this wave, okay, this wave is providing some energy. By means of that energy, this medium particle is vibrating in the upward direction. Let the displacement of this medium particle's vibration be y, you take, that is y1. Y1 is the displacement of the medium particle's vibration. Now, at the same time, the second wave is coming. When the second wave comes over here, even the second wave also will provide some energy to the same medium particle in the same direction. Remember. Then what happens over here? The second medium particle means the crust is, there's a falling on the crust of the first wave. Trough of the second wave is falling on the trough of the first wave. Crust of the second wave is falling on the crust of the first wave. Like this, if at all, the mixing of these two waves takes place. But this is one category. One more category is also there. That we will discuss later. Okay, in this category, what's happening? The crest of the second wave is falling on the crest of the first wave. Trough of the second wave is falling on the trough of the second wave, like that. So by means of the second wave, same medium particle is given another energy, new energy in the same direction. Then what happens automatically? Will the medium particles displacement increase or decrease? You are sleeping. You are sleeping. You are sleeping. Mayur is sleeping. Yes, sir. How can you say, sir? We are looking at you now. Since the beginning, you have been observing that our eyes are kept open. How come you say like that? That also is practice. Okay, whenever we get here, how we swallow, and in the same way, sleeping. Okay. And we will be thinking that the body is awake, but he will be sleeping. Okay. Okay, for past half an hour, so Sagar's position is this one. Sagar's state is this one. Understood? Okay. Right. Yeah, the question. Remains same means the same in sleep. Remains same means you are sleeping in sleep. See, this is the medium particle. Okay, the first wave is coming over here. By means of the first wave, what's happening? So the medium particle is given some energy in the upward direction. So by means of that, the medium particle is exhibiting some displacement. Now at the same time, second wave is coming. Okay, the second wave is also providing the energy to the same medium particle. Okay, in the same direction. Then will the displacement increase or decrease? It increases. How come it is okay? Same particle is given push 2 times man by 2 energies. Now understood? Same particle is given energy 2 times. Yes or no? And then what happens over here? Okay, the displacement increases. Yes or no? The displacement increases. Understood? That means the same displacement. So that's the unit I understand. Like this. Okay. Understood? Only one direction. Only one direction, not 2 directions. Okay? That's what he is thinking, 2 directions. Okay. Okay. So only one direction, like this. Okay, so like this, immediately what happens by means of S1 upward direction, by means of S2 upward direction, then the resultant displacement will increase. The resultant displacement will increase. Am I correct? Okay, so by means of this, here you see, by means of the second wave, so displacement is, so why do you say? Since these two displacements are in the same direction, got it? Okay, so what is the resultant displacement over here? Y1 plus Y2. Y1 plus Y2. Y1 plus Y2. Understood? Okay, so that means if at all these two are having the same displacements, means Y1 is equal to Y2. So that is Y, say. Then the resultant displacement is equal to Y plus Y. So that is 2Y. Maximum displacement. There is a maximum displacement. But so in this type of superposition of waves, ultimately the maximum displacement is obtained. Whenever the maximum displacement is observed, if you put any screen over there, bright band will be seen. Bright. Illumination increases. That is called constructive superposition. This is called constructive superposition. This is called constructive superposition. Constructive superposition. Understood? Okay, so one more type of superposition also takes place. Okay, so what is that? Look at this here. I will be taking two sources of light. This is the source of light S1. Okay, so there is a medium particle over here. By means of this medium particle is made to vibrate in this direction. Therefore, one wave is produced over here. This is the wave which is produced. Okay, now the source S2 I have taken very close to this. Now, what about the wave which is coming from S2? How is it superposing? The trough of the second wave is falling on the crest of the second wave. Means like this, the mixing of the two waves is taking place. The crest, the trough is falling on the crest. Next, crest is falling on the trough. Okay, next crest, so trough is falling on the crest. Like this, the mixing is taking place. Right? In this type of mixing, what happens? Look at this. This medium particle is given energy in the upward direction. At the same time, the second wave is coming. The second wave is providing energy to the same medium particle in the downward direction. The downward direction like this. Let the displacement by the first wave be Y1, the displacement by the second wave be Y2, then the resultant displacement is equal to Y1 plus minus Y2. Y1 plus minus Y2. And if at all these two displacements are same, that means if y1 is equal to y2, that is fine. Same. Then, so what happens? So this is y plus minus y, 0. Y plus minus y, 0 means no displacement. Means dark band here. So whenever the superposition takes place in this way, that is known as a destructive superposition. We call destructive superposition. We call. This is called a destructive superposition. This is called a destructive superposition. Destructive superposition. Come on, please make a note of it. Make it faster. Okay, now we will be discussing something about interference. See here, superposition has taken place now. Right? Superposition means that is the combination of the waves. Right? Whenever superposition of waves takes place, there is a possibility of having three important things. What are they? The very first one is when the waves of same frequency, listen to me carefully, when the waves of same frequency moving in the same direction superpose each other, what happens? There is a physical phenomenon takes place. When the waves of same frequency moving in the same direction, superpose each other, then what kind of physical phenomenon do you get? Then what kind of physical phenomenon you get? When the waves of same frequency moving in the same direction superpose each other, then what do you get? Interference. That is a condition for interference. Interference takes place. That is the first case. Interference takes place. You underline this interference. Okay. You underline interference. Okay. So the next category, look at this. When the waves of same frequency, moving in the opposite direction, superpose each other. Then what do we get? Yes. What do we get? Waves of same frequency moving in the opposite direction superpose each other. Then what do we get? No idea? No idea? Stationary waves are formed. Stationary waves. Stationary waves are formed. Stationary waves are formed. Stationary waves are formed. Stationary waves are formed. Okay, next. The third category is, look at this. Now, in the first two categories, we have taken the waves of same frequency. Waves of same frequency. Okay, now in the third category, what I do is I will be just taking the waves of slightly different frequencies. Right? Third category, when the waves of slightly different frequencies. Slightly different frequencies moving in the same direction. Moving in the same direction. Superpose each other. Superpose each other. When the waves of same frequency moving in the same direction superpose each other, what happens then? Any idea? When the waves of slightly different frequencies moving in the same direction superpose each other. Yes, Sachin. Constructive interference. Any more answers, please? Then, beats are beats are okay. So these beats, okay. So also happen in sound waves. So did you ever see? So there's a beat formation and other things. By means of these beats and other things, what do we do in practical? There is a practical application. The tuning of musical instruments takes place by means of these beats. Okay, so did you ever observe any musical concerts? Musical concerts. Musical concerts. Not Alan Walker or so the BTS. BTS, you know? BTS. You know, everybody knows. Koreans. Girls. You don't know. Good. Okay, so not those musical concerts. Our Indian classical musical concerts, have you seen? Yes? Okay, so did you ever observe at the beginning of the musical concerts? Okay, so there's a musical instruments will be there, tabla, mridangam, and all the things at the beginning of the musical concerts. Okay, before the program begins, so there's what do they do? Did you ever observe? The players, okay, so they will come to the instrument, they will be having a small hammer. They will be bringing with them. Okay, there's a tabla and mridangam, there's that membrane will be there. No, that membrane will be having some, okay, just like the nylon threads and all the things. Okay, that's why screws will be there. So screws they will be tightening. Okay, they will be hitting like that. So they will be hitting like this. Okay, that is called tuning of the musical instrument. And whatever the frequency, okay, so that singer or remaining instruments are going to produce, this particular musical instrument has to correlate with that. Otherwise, what happens? That will not become music, that becomes noise. Noise, music, noise, both the things are opposites. When it is in phase, that becomes musical. When it is out of phase, noise. So that's why tuning of the musical instrument is very, very important. Okay, so this here, so they will be doing like this. They hear, they put their ear also. That's like that before the program begins. Before the program begins, they will be doing like that. So what do they do by means of this? Tuning. Tuning means by means of beats only. The beat frequency they will be observing. The beat frequency they will be observing. Suppose difficult you take Veena, so there will be there's some knobs over here. So by means of those knobs, the strings they will be tightening. So by means of beat frequency. By means of beat frequency, that's they will be. So they know, we don't know that because they will be. That's they work on that particular instrument. They know very well how the beat frequency comes and other things. Got it like this. So here you see beats are formed. So these three conditions are very, very essential. Now interference. That's what we need to understand. So what do you mean by interference? This is what we have to come now. What do you mean by interference? What do you mean by interference? Now, in the first case, I have told you that interference is a phenomenon in which interference is a phenomenon in which two or more waves of same frequency moving in the same direction superpose each other. That is called interference. Now, there was a scientist, Thomas Young. Y-O-U-N-G. But when Young's modulus, same person. But Young's modulus will not come here. This is right. That is mechanical properties. Got it? Thomas Young, he conducted one experiment. That is Young's double slit experiment. And in this interference, there is a condition. If at all you want to obtain interference phenomenon, there is a condition. So what is that condition? Waves of same frequency, I have told no. Same frequency of waves, how do you generate? Same frequency of waves are to be produced. How is that possible? How is that possible? What's it? Taxi. You ask Shivara sir to provide some wheelchair, that's some easy chair. So the same old people will visit him. Easy chair. Even $500 easy chairs are available. You cost just 500, 600. You tell Shivara sir, that's a deal. Purchase. But for easy chair, Shivara sir is okay. Now you are going to pay. You see, that's a fellow that's got ready to bring an easy chair. Go. You are in emergency steps. Go. Abhishek. I should not stop emergencies. I should not stop emergencies. Right. Yes, right. Now this is the same frequency we have to produce. And how to produce the same frequency? There must be some arrangement. So that arrangement, that is called coherence. There is one thing, that is a coherence of it. Coherence of it. So what do you mean by coherence? Coherence is a phenomenon in which two waves are produced without any phase difference. You may ask one thing. So without phase difference, how come it is sad? There could be some phase difference initially, but remember, what about the phase difference which is present in the beginning? Same phase difference should be present. So constant phase difference, that is called coherence. Now the thing is how to bring those coherence and how to bring those coherent sources. Got it? So for that, Young, he made one arrangement. That is called a double slit experiment. Double slit arrangement. So what he did was, look at the board. What he did was, here you see, so he took one slit, very narrow slit over here. This is a primary slit. That is this. Right? Now, this is the axis of this. There is a screen present over here. Right? Now, we need to bring one more screen over here in this way, which is opaque. Now, you need to make some narrow slits over here. It's very narrow slits. This is one slit and this is one more slit. Nice. Now this slit you need to illuminate by means of some light. Then what happens from here? Spherical wavefronts will be coming out. These spherical wavefronts will be just passing over here. These are the spherical wavefronts. Right? Now, the distance between this is what you say, and this. This is S1 and this is S2. Distance between O S1, O S2, both the things are same. Understand? Therefore, the means yes, S1 distance, yes, S2 distance will be the same. Therefore, these two slits, S1 and S2, will get illuminated simultaneously at a time. Therefore, from S1, the secondary wavelets are produced. Okay, look at this. The secondary wavelets are coming out. Okay, so even from S2, okay, the secondary wavelets are coming out like this. Very nice background music Sachin is giving. Good, very good. Because I am talking now. So the cinema is going on, some background music is taken. Otherwise, got the point? Emotions and other things is not. Emotions, okay? Right, background music. So music is very, very important for anything. So in that way, it's here. So Sachin is giving me background music. Background music. Okay, so look at this. Here you see. So these are the secondary wavelets coming from S1. These are the secondary wavelets coming from S2. Now look at this. Here you see. This is the point where these two waves are interfering. This is the point. This is the point. This is the point. Like this, we come across many points where the interference of these waves takes place over here like this. Understood? Okay, so will that interference be constructive interference or destructive interference? Constructive interference or destructive interference? And if at all constructive interference takes place, then if at all constructive, what man? This a light. This fan is that, but this also there's a reading. So what did you do? Without switching off, that's only just in the eyes you control. What man? Abhishek. Sit down, sit down. Right. Yes. Good. Okay. See this here you see. So this whatever the interference take place over here. These interferences could be constructive ones or destructive ones. If it are constructive interference comes over here, then bright bands are obtained here. Ultimately, what do we get on the screen? The combination of bright bands, dark bands, bright bands, dark bands. But so that is called interference pattern. Okay, so there's a fringe or band. Both things will be okay. That's equal. Both the things will be the same. Understand? Okay, now this here. This is how interference takes place. Now we need to understand the conditions for the formation of a bright band and the condition for the formation of dark band. Look at this here. You see. So this is the point. That is O dash. You say. Now the distance between S1 O dash and the distance between S2 and O dash, both the things will be the same. So look at this. S1 O dash is equal to S2 O dash. S1 O dash and S2 O dash. Am I correct? Okay. Now by means of this, what happens? Whatever the wave which is coming from S1, the wave is reaching over here. Next, at the same time, without any time lag, that means without any phase difference and path difference, the light will be reaching over here. And whatever the two light waves which are reaching to the point O dash, that will always be constructive interference. Always a bright band will get formed over here. Bright band. Bright band formation. So O dash will always give you a bright band. But what about the remaining bands? Okay, the remaining band could be bright one or a dark one. Anything. Usually, so when the bright band is obtained over here, this is the point O dash. Okay, so this is the bright band. Next, the dark band will be here. Next, the bright band will be here. Dark band will be here. Next, the dark band will be here. Like this. So the series of bright and dark bands will get formed. The series of bright and dark bands will get formed. Right? Okay. Now, if at all you take any other point, not the central point. This is called central maximum also this is. So this is called central maximum. Central maximum we say. Okay, so if you take one point P over here. Now at point P also there will be some band, no? Will it be dark one or bright one? We can't say. Anything it could be. That completely depends upon the phase difference or path difference. Phase difference and path difference. Okay, now let's look at this here. You see, so one wave is passing over here like this from S1, right? So in this case, okay, so the distance between S1P and the distance between S2P, so are both equal? Are both equal? Okay, they're not equal. Got it? Okay, so S1P is less than S2P. S1P is less than S2P. That means what about the light wave coming from S2 to reach the point P? The wave has to travel longer distance than the wave coming from S1. Than the wave coming from S1. Are you understanding? Got it? Okay, so S2P is more than S1P. Okay, then what happens to the wave which is coming from this S2 will have to cover longer distance over here. Longer distance over here. Understood? Now we need to establish the conditions for the bright band and dark band. In what way? Look at this. So the wave which is coming from S1, so I will be representing as Y1 is equal to same frequency. Means the amplitude also will remain the same. So there is A sine omega t you say. Next, whatever the wave which is coming from the second source, S2, this can be represented as A sine omega t plus phi. Omega t plus phi. What is phi? Phase difference. Because there will be some phase difference. There will be some path difference. There will be some path difference. Understand? Okay, so A sine omega t plus phi. Now, what is the combination when these two waves get combined with each other? So, what do we get? Y1 plus Y2 over here. So, Y is equal to A sine omega t plus A sine omega t plus phi. Right? Okay, so you write up to here. That's not over our discussion. Please make it faster. Even this figure, freehand figure you draw, make it fast. Over. Right? Now, these equations we need to continue. Okay. So look at this. Can you erase this? Huh? Girls. Y, which is the resultant displacement. The resultant displacement capital Y is equal to, I will be taking A as common, sine omega t plus, that becomes a sine omega t cos phi plus cos omega t sine phi. Okay, right? From these two things, sine omega t I will be taking as common, including A. A sine omega t 1 plus cos phi plus A cos omega t sin phi. Right? Now, A into 1 plus cos phi. Put A into 1 plus cos phi as capital A cos theta, where theta is the combined angle of phase difference. Next, A sin phi. Yes, A sin theta, I will suppose. If I write these two things in this equation, what do you get? Capital A sin omega t cos theta plus capital A. Have you written this one? Huh? Capital A cos omega t sin theta. Now did you understand? Now A y is equal to A sin omega t cos theta plus cos omega t sin theta. Sin omega t plus theta, where capital A is resultant amplitude, where A is equal to resultant amplitude. Resultant amplitude. Capital A is equal to resultant amplitude. Resultant amplitude. Got it? Okay. So now let's look at this here. By means of this equation, what do you say? Even the combination of the two waves is nothing but simple harmonic by nature. So this is simple harmonic wave. Whatever the combination these two waves are giving, that combination is ultimately simple harmonic by nature. Simple harmonic by nature. Got it? Okay. So this is the equation where this is the equation 1 you take, this is the equation 2. By squaring 1 and 2 and adding. So what do we get? A square cos square theta plus A square sin square theta is equal to, okay, small a square 1 plus cos phi whole square plus A square sin square phi. Understood? From these two things, A square can be taken as common. Cos square theta plus sin square theta 1. So this becomes A square. Now, again from these two things, A square can be taken as common. A square. This is 1 plus cos square phi plus 2 cos phi plus sin square phi. So cos square phi plus sin square phi 1. 1 plus 1 2. 2 plus 2 cos phi. 2 again can be taken as common. But look at this. A square 2 A square into 1 plus cos phi. One plus cos phi. How do you write? Trigonometric equation. 2A square 2 cos square phi by 2 cos square phi by 2. 2 into 2 4. A square is equal to 4 A square cos square pi by 2. Okay, so I will be multiplying by the constant or either sets. K square 4 K square cos square pi by 2. Understood? So K square. Intensity of light I is always directly proportional to square of the amplitude. So I is equal to K into E square. This is after interference. And before interference, initial intensity I naught. Okay, so this is the intensity of the combination after interference. 4 I naught cos square pi by 2. Now you need to discuss whether this intensity is maximum or minimum. That completely depends upon RHS. 4 I naught cos square pi by 2. That too on cos square pi by 2 only depends. Cos square pi by 2 in the sense, look at this, if the value of this complete cos square pi by 2 becomes 1 somehow, then I is equal to 4 I naught. Why 1? I said because in the cos function 1 is the maximum. In the cos function 0 is the minimum. If the complete cos square pi by 2 becomes 1, okay, then what happens? I is equal to 4 I naught. So you may ask, sir, minus 1 is also there. No, cos 180 is equal to minus 1. And minus 1 is less than 0. No, minus 1 is also maximum in the opposite direction. In one direction, if okay, it is maximum. In the opposite direction, it is maximum. Minimum is 0. Minimum is 0. Remember, and all remaining values lie between 0 and 90. 90 and 0. Cos 0 is 1. Cos 90 is 0. But okay, now here you see when cos square pi by 2 becomes 1, then I is equal to 4 I naught. There is maximum intensity. But so maximum intensity means there is a constructive interference. When the maximum intensity is okay, so this is obtained, then on the screen one bright band is obtained, bright band formation. And if now cos square pi by 2 is 0, then what do you notice? Then what do you say? Cos square pi by 2 is equal to 0. I is equal to 0. I is equal to 0. The means of dark band formation means intensity becomes 0 or intensity becomes minimum. Intensity becomes minimum. So that discussion is very, very important. Problems and questions will be composed based on that discussion. Remember. But see here I will write. So here you see when cos square pi by 2 is equal to 1. Then I is equal to 4 I naught. So this represents maximum intensity. So this is the condition for bright band formation. Bright band formation. Okay, so this is the condition for constructive interference. This is constructive interference. So for this constructive interference, this complete cos square pi by 2 value has to become 1. Has to become 1 means that is decided by phi. So for this, phi should take the values. What kind of values are possible now? Phi should be pi. Next 2 pi. Next 3 pi. And so on. So phi should be okay, not 3 pi, 4 pi. Understood? Okay, so that means phi should be the even multiples. Okay, so even multiples 0. Okay, so this must be 0. But if this is 2 pi, 4 pi times. Okay, then phi is 0, cos square phi 0, 1. When this is 2 pi 0, 4 pi 0. Are you getting my point? Yes or no? Okay, so that means what do you say here? Phi takes the values even multiples of pi. Even multiples of pi. Even multiples of pi. Then path, this is called phase difference. This is called phase difference. Okay, so when 2 pi phase difference is there, remember, look at this in the wave formation. So the distance between this and this, phase difference is 2 pi. The corresponding path difference delta is called lambda. Lambda is the path difference. Lambda. Okay, so this is path difference delta is equal to 2 pi n into lambda. So this is the path difference. Phase difference is 2n pi, and the path difference has to be m lambda. Under these conditions, what happens? Right band formation takes place. Right band formation takes place. Come on, note it down, this one. Now you need to discuss something about the dark band formation. The dark band formation. For the dark band formation, what has to be here? Look at this. For dark band formation. For dark band formation. Right? So cos square pi by 2 should become 0. Okay, 0 in the sense of, okay, so what are the possible values for pi? So that implies I should be equal to 0. Minimum of 0 intensity. Minimum of 0 intensity. So for this purpose, pi should take the values pi. Okay, so next to 3 pi. Next to 5 pi. So that is 2 n plus 1 into pi. So that must be the phase difference. The phase difference in this particular case, okay, so phase difference pi should be equal to 2n plus 1 into pi. Then what is the path difference, the corresponding path difference? The corresponding path difference delta is equal to 2n plus 1. So when pi is the phase difference, the corresponding path difference will be how much? 2 pi radians is equal to pi lambda. Then pi is equal to lambda by 2. So 2n plus 1 into lambda. So this becomes the corresponding path difference. Okay, so during the interference, whenever we come across the phase difference of 2n pi and path difference then lambda, that will be the indication of right band formation, which is called constructive interference. And during the interference, whenever we come across a phase difference 2n plus 1 pi or path difference 2n plus 1 lambda by 2, in such cases, dark band formation occurs. Dark band formation takes place, which is a destructive interference. Which is the destructive interference. Understand? Destructive interference. Yes, over like this. So in this interference, there is a small topic, there is a bandwidth formula also we have to discuss. Bandwidth. Very good. Okay, so what is the time now? Akhilesh is telling something? Akhilesh. You are telling something? Time? Ah. Okay. So this another time is 5 o'clock. Okay. So that's actually it's again even in this chapter also you will be writing the test tomorrow. But understood? So we will do one thing. Test when will you write in the afternoon session? Okay. Wait. In the morning session, so I will be completing the remaining part of this and diffraction and polarization, and I will make you work out some problems. Didn't go? That's not the way. Maybe. Okay. Right? So test. This is usage of. Okay, so what I'm telling you is tomorrow in the morning hours, otherwise would you